Hi there, if you can just announce yourself and just for the register. So we're gonna make a start in a few minutes. Hi Charlie, hi Hayden. Hi Corey, good to see you. Hi Harry. Amy, hello, hello Luke. Hi Dick. Okay, it should be okay now. We should all be back up again. Um, right, everybody has disappeared. Let me see. Just wait a moment until everybody's back again, hopefully. So 6 up. Okay. Anyway, if okay, if just looking at the the controls, everything seems to be okay. Right. Okay, I'll just carry on. I hope that the others are 16 now, so we are back in business. Okay, this talk is about taking measurements, and again, sorry for the disruption. What I need to do when it disrupts sometimes, and it seems to fix it, I just need to switch off the control software, and then let it kick back in again. And once it reconnects, it seems to sort itself. That's what I've noticed. So the whole process takes about 3 minutes. Should it happen again, just hang in there for a couple of minutes, and it should be we should be back in business. Anyway, you can see it later as well when it's recorded. So this is the not the last lecture for 315, but it's the one before the last lecture. There's just a tiny one after this to not tie all the loose ends together, but to look at the last two criteria, and then we've just got the summary at the end of it. So this is about taking measurements and actually doing it. And then we're looking. Previous one we looked at meters, all the different meters we have. Now we're looking at taking measurements and the issues we have. Some of it we discussed before, so there may be a little bit of repetition, but some of it may be new to you, and some of it you may be doing at work anyway. Okay, this is the criteria. I took 2.7 and 2.8 out, even though we're going to touch on it, but we're going to cover this in the next presentation. Okay, next one. resistance measurement, and I think I mentioned this before, that whenever you measure resistance, you've got a small voltage which comes out of the meter, and obviously it's a problem as well. The whole idea is you put a voltage through, small voltage is put out, small current flows into the resistance, just a tiny amount, and then the either the current is measured or the voltage drop is measured against a known resistance, and so the meter can determine what the actual resistance is. Yeah, so this is how an analog meter would work. Digital meter is going to be similar. Anyway, for an insulation test, you use a lot higher. You use a voltage which is a lot higher than the voltage for a normal digital meter. So for digital meter, we're looking maybe at about a volt, possibly even less than that. It depends on what meter you're using. For an analog meter, it's typically about 9 volts. And most analog meters, you have to tune them in as well. So if your battery dies down a bit or goes down a bit, you've got like a little potentiometer. So you tune in the meter for full-scale deflection, and then you take your measurements. Okay, very important. So there are a couple of implications. One of them is if you try to take a resistance measurement on a live circuit, it doesn't work because inevitably there might be some signals present, and they might skew up the signal you're trying to measure on your meter. So don't do it. That's the thing. So make sure that you only measure something on a dead circuit. So it can only be done on dead circuits. Voltage present in the circuit will falsify any data the meter shows, so you can't rely on it. Other than that, I mean, especially when you use an analog meter and you've got 9 volts, if you imagine you've got a circuit that's based around 5 volts, it potentially could destroy components. The other thing as well is when you've got a dead circuit, so it's not powered up, there's no power going into the circuit, but you've got a lot of components which are sort of in the circuit. Some of the components may be in parallel with the resistance you're trying to measure, and if that is the case, you will get wrong readings. Yeah? So you have to make sure that you take the component out, or the components are isolated, in whichever way you do it. If you need to measure a resistance, it's just something to be aware of. Also, temperature will impact resistance values. Just something to bear in mind. Most items you're likely to measure, or components you're likely to measure, are sensitive to temperature changes, and I'm talking extremes now. So if you measure something at, let's say, -5 degrees, you're going to get different readings as when you would take the same measurement for a component that's just heated up and it's at 50, 60 degrees or something. So again, that's something to bear in mind as well. Right, Callum Sam, hi there. Thanks for checking in. Next slide. Resistance measurement. Performing the insulation test. So low voltages for a resistance test will only show the resistance of a material at that voltage. So that's important. So the thing is that, and you can see this, I'm not sure whether we did an experiment in class. I did it with some students. When you take a measurement from, for example, if you've got water, and you take a measurement just using a low voltage, the resistance is actually quite high. I mean, you would think water is a conductor and all that, but it's fairly high, especially if it's not saline water, if there's no salt in it. When you increase, for example, when you use an insulation test and you try to figure out what the resistance is, you get like very different results from an insulation test. It virtually goes down to 0. So if you use a high voltage, it sort of whatever's in there and generates some sort of resistance seems to break down instantly compared to just using a volt or something where you get fairly high readings. Insulation tests have to be done above the maximum voltage the insulators are designed to be used for. So, for example, if you use a 3-phase system, you've got 415 volts, and again, that's just the RMS value. RMS stands for root mean square. So in order to get the peak voltage for the waveform, we have to multiply the RMS voltage by 1.41. and then we end up with about 600 and a bit volts for a three-phase system, and for a single-phase system it would be 240 volts times 1.41, so it would be 390 something. Yeah, so it's about 390 volts. So on the insulation tester, you've got two settings. One is for 500 volts, one is for 1000 volts. To have like a genuine idea of whether the insulator is going to be okay for example, your single phase supply, the minimum voltage you could use to do this test is 500 volts in order to have a meaningful test result. For a three-phase system, it will be 1000 volts in order to get a meaningful result. Yeah. If you do 500 volts, the peak value is going to be a lot higher than 500 volts. And so you would have to use 1000 volts. Bearing in mind that the testing voltages are not AC, they are DC. So you apply DC voltage across the insulator to make sure it can stand it, and it works fine. So my experience generally is that at about 1000 volts, sort of electricity starts jumping. Yeah? So if you've got a tiny crack somewhere in an insulator, it'll just arc through the crack, and you sometimes can't see the crack. But and that's normally happening at about 1000 volts. And then when you look at 2, 3, 4 kV, so electricity becomes very jumpy. I don't know whether that's a technical term, but it's very much more dangerous. It's a completely different ball game to deal with once you go over 1000 volts. Below 1000 volts, you again, don't take my word for it, and there's no science behind it or anything. It's just experience. But below 1000 volts, it needs to be some form of contact, either through a chemical or like water ingress or something like that, or two items need to touch one another. There needs to be some sort of contact to get a breakdown in the insulation, or you need to touch it to get a shock or something. But at 1000 volts and above, you don't even need to touch it, and it'll just arc over. Okay, it's just something to be aware of. Let me just check the systems here. Everything is still okay. Good. Problems with resistance tests. Yeah? So if you try to measure resistance, one of them is you can have dirty probes. So if your probes are fairly old, and what you find is, just follow the mouse, you can see the probes here, that sometimes when they get old, they start getting, you pick up grease or some chemicals or things like that, and you don't get a good contact. And sometimes, especially when you look at small components, it's sometimes hard to get a decent contact to get some measurements, and you think the component is dead, but all that's happened is that you didn't get good contact. It's also the contact surfaces. So whatever you try to measure, they start corroding. You get all sorts of problems in there. If you ever take an oven apart from in a kitchen or in a catering environment, the amount of grease and stuff like that gets on there is just phenomenal. It gets all over the place, and obviously people don't clean inside an oven where you may have contacts. And so you get like very often dirt on the contact surface, which will not give you a proper resistance test or an indication. The other one, which is quite interesting, and it's a big problem in pad testing, when they look for earth continuity, there's something called like a contact current, and when you've got a high current, it tends to generate a better contact. So for example, in pad testing, this portable appliance testing, one of the big jobs is to make sure that the earth lead has got continuity, and that it can withstand a high current, a fault current, without blowing up. So there used to be about like 10 amps, 20 amps, 15 amps. And modern portable appliance testing equipment, it just checks for continuity to see whether it works. But the problem they have is they get a resistance reading, and when you use a low voltage and a low current for this resistance reading, you sometimes don't get the contact current. That's what they call it. And the resistance reading is fairly high, so it might just be an ohm or something. Whereas with a good contact current, where you put the terminals together, they touch, they make contact, and as the current goes through them, they attract. They almost like a magnet. They stick together. They get good contact current, and then the resistance actually goes down a little bit further. So you might only get like a quarter ohm of resistance for the earth continuity lead, or for the earth lead. So that again can be a problem, because you're looking at tiny amount of voltages you're using, and so it's like a current that's in the order of milliamps, or even less than that, as opposed to some portable appliance testing equipment, which has got several amperes to make a contact, 5 amperes, 10 amperes, and so on. Resistance in series can be higher, so if you've got like any I don't know, it's something to look out for when you try to measure something on a circuit board, and sometimes it's very difficult to see how the tracks go, because you might have tracks on top of the board and there's some tracks underneath the board, and you've got some components on there, and you think, okay, there's nothing in parallel, so I can test this component, and sometimes you try to find some points where you're connected, and there might be, without you realizing, it's something in series, and you get like a higher value. So it's always a problem whenever something is inside a circuit to measure resistance. So at least you would have to take one side of the circuit, of the component, off, away from the circuit, so that you can take a measurement which is meaningful and means something. When you look at three-phase motors, it's like the thing, you have to take off the little connecting strips, what are they called? The little plates, terminal plates. You have to take them off, and then make sure that you're not measuring the resistance of two coils, or two coils in parallel with one coil, but that you are measuring each coil on its own. Then we've got also a problem, voltages in the circuit, we already talked about this, but sometimes the meter can be out of range. So when you use a box standard meter, like a DMM, then very often they only go to about 2 million ohms. But if you want to measure resistance, you might need a meter that goes up to 15 million ohms or even higher, to make sure that the insulators are okay. Now, an insulation tester will normally have a very high resistance reading, so it'll go up to several million ohms. And normal DMM, if it's over 2 mega ohms, you're not that interested anyway. You need specialist equipment for that. Also, in the lower section, so you tend to be able to measure down to about 100 milliohms. But if it's any lower than that, you would have to have specialist equipment again, so it would be out of range. Right, just looking at the chat room. Ross is here, Alex is here, hi. Thanks for checking in. And Callum as well, I think, has said so in some before. Okay, current measurements, current flow through a circuit. So that's very important. Yeah? And I think this is one of the biggest problems I've found in my years of teaching, that people are getting it wrong. And I've had a few episodes as well where, I didn't break anything, I just blew fuses, where I left the leads in the wrong terminal socket, and I didn't realize I was just taking the meter out, taking a measurement, and then car battery, and then the fuse blew, and I had to get another fuse, to make sure that the current meter still works. But it happens very quickly if you don't pay attention. So for current measurements, first of all, it's the current flows through a circuit. Yeah? For voltage is always across a component or across a circuit. So if you measure voltage, you always measure across, and ideally, the circuit is powered up, otherwise there's no voltage there to be measured. For current, you have to actually break into the circuit in order to take a measurement for your current. So in other words, it cannot be measured by putting the probes across a supply. And this is, standard mistake students do when first time they get exposed to using a DMM. And that is that you're asked to measure the voltage across a circuit and the current the current through a circuit. And it's easily done. You just take your meter and you think, yeah, it should be okay, or maybe you don't think, and you just put it across a power supply to measure what current is there. Now, if the maximum current the power supply can supply is something like 5 amps, and you put it in the 10 amp socket, you will effectively generate a short circuit and you will get about 5 amps. I mean, some of our power supplies you can control the current flow. You get a maximum of 5 amps coming out of it, and it won't blow the fuse. If you use a car battery can supply, and this is what's happened to me recently, how many amps? I don't know, 500, 600 amps instantaneously for a short period of time, for the starter motor to kick it off. And anyway, I just wanted to measure, whether the car battery was in reasonable nick, what the voltage was. And normally you can start an engine if it drops down below 12 volt, it should still be okay, maybe 11, 11.5. Because any lower than that, then that's very often no chance of starting the engine, so you may as well just charge it up. And I think the problem you've got at the moment is a lot of people with the lockdown, they leave the car at home. They don't use the car for weeks, but you've got your central locking, you've got the alarm, a few other things in the car, and they constantly drain the battery. And so when they get back into the car, very often the battery has dropped down to about 10 volts or something, and it's not enough juice to keep the starter motor going. And anyway, same thing here. I just wanted to check what the state of the battery is. And I was doing some current measurements before my meter and totally forgot about this. And I had the lead still plugged into the current socket, the ampere socket. And even though the meter was turned to voltage, it's still like a short circuit, and I blew the fuse inside the meter. It's not a great deal, but it's just annoying, especially when you want to do some measurements afterwards and you haven't got the fuse handy to replace the fuse. But it happens very quickly. Old meters, a bit more dramatic. They were unfused. You had like an unfused 10 amp circuit in there for measuring your current. And if you use them on a car battery, they would just blow up. They would just go up in smoke, literally. So you have to be very careful what you're doing. Okay, so what have we got? Where were we? The circuit has to be broken, current has to be redirected through the meter, unless you use a clamp meter. We're going to look at a clamp meter in a minute. There's a limit to the maximum current a DMM can measure, and it's somewhere between 10 amp and 20 amps, for the models I've seen so far. 10 amp is probably for most models. I've seen one or two on 20 amps. And again, for electronics, it's okay. For industry, it's just not enough. The types of current you're dealing with are a lot higher than that. Okay, next one. This is the way it should be done. So I've got this diagram. So you've got your supply, could be DC, could be AC. Then you go from the supply into the, that's your red lead, into the meter, and then the ampere input, and then you've got your common output, and then that's where current comes out, and then it goes through the load, and it goes all the way through, and you'll get a current reading. So you measure your current, and obviously the unit is in ampere. Okay, the meter, and this is where the nightmare kicks in, and I think Callum mentioned this before yesterday, where students were at college where he was, and students were doing measurements and were blowing fuses all the time. Was it you, Callum? Just give me a sign of life there. And so you've got the black lead, which goes into common, and then normally your red lead would be into volts, ampere, or in this instance it's for revolutions per minute as well. And that's most of the time what you will use it for. But when you want to measure current, you've got the milliamp input here for milliamps and microamps, and for ampere. And if we look very closely, I don't know whether you can see this on the computer, the maximum current you can put in here is 10 ampere. And milliamps is probably a couple of hundred milliamps, 200 milliamps or something on most meters. And the difference between the two of them is that obviously the resolution is different, and you can see as well you've got two settings here. You've got one for milliamp, one for microamp. And I'm just trying to think, is it just for AC? It looks like this meter just works on AC for those. Some meters they've got on the top like a separate button where you can toggle between AC and DC. Just looks for AC, in this instance. Okay, but anyway, you would have to then take your red lead and you unplug it from the voltage, ohms, and in this instance RPM, and you plug it into the ampere meter, whether it's a big current or a low current. And then most of them are fused as well, so they've got like a 10 amp fuse in there, and there would be a 200 milliamp fuse. I think it says 400 milliamps on this one, so maximum current is probably 400 milliamps you can measure. So you've got two types of fuses in there, and that's sort of protecting you. In the olden days, you had unfused meters as well, but I haven't seen them around recently, so maybe they've gone away from that completely. Okay, move on. What to look out for current measurements, I for current. The resistance between the red and the black of the DMM when in ampere measurement position is 0 ohms. Or 0 ohms would be ideal, but probably about like 0.1 ohms or whatever. But the resistance is very, very low. So it's de facto like a short circuit. So if you put it across something, for example, across a power supply, when you try to measure current into the circuit, you would generate a short circuit. It's not, unless the power supply, most power supplies today are protected. If it's not protected, it's a problem, and most likely you're going to blow a fuse in the meter. But so you have to break into the circuit. Also, one nightmare is, and I think okay, I got the response from Cullen. Yes, it was at your college, and Cullen was blowing the fuse. Not just Cullen, loads of people, myself as well. I have to put my hands up. I've done the same mistake many times, but it's just negligence, not looking, and familiarity breeds contempt. I think this is sometimes a problem. You are too familiar with the stuff, and you just slap it on, and you don't look properly, you don't pay attention, and then stuff happens. Okay, we went through this question: what would happen if you measure a current across a supply? The fuse would blow. One way as well is to check out meters to see whether the fuse is blown or not. Is you just let me go up. So on this meter, which you use for the current measurement, you put the black lead in common and the red lead into ampere. And then inside you would just have like a piece of wire with a fuse in the circuit. And then on the other side you would get a meter as well, and you put it into common and into resistance. And you measure the resistance. And if the resistance is 0 or near enough 0, and you get continuity, then the fuse is still intact. It's okay. If you don't get a reading at all, and it's like an open circuit, like if you use a continuity tester between this point and that point, and you don't get continuity, or you don't get, you just get a very high resistance, then the fuse is blown. And that's sort of one of the first exercises when, when you come back, will we do current measurements? Probably, if you've got some time. So this would be one of the jobs I would want you to do as well. So I would come with a handful of fuses and a couple of screwdrivers, and then we check the meters before we do any current measurements to see which ones are okay and which ones are broken. And the thing is, the way fuses go these days, there's no bang, there's no smoke, there's no nothing, so they just die silently, and so you don't know that the fuse is gone until you measure it. But that's the trick, okay? So you take this meter, one lead in there, and on the other side you've got a resistance meter. Low resistance means fuse is intact. High resistance means fuse is blown, and you need to change the fuse to get a current reading. Okay, I've done that. Right, what to look out for by measuring current. Ensure the leads are in the correct sockets. Very, very important. I messed up with that quite a few times. Ensure that the fuses are not blown. How do you do this? I just told you how to do it. Ensure that you've broken into the circuit and you are not measuring across a circuit. Very, very important. That's one of the most common mistakes which is done. Avoid using unfused current inputs. So if you've got an unfused meter, like an old one which you've come across, try not to use it because it can be quite dangerous. Shall I tell you the story? I'll tell you the story. I'm not sure how long ago it took place, and it's a story which was told to me by a colleague about how many years ago? 20 years ago, probably about 20 years ago. And he was a fellow lecturer, but he was working in the power generation industry, so at a power plant. And at his plant, one of the guys, he took a voltage reading from the generators, just to see how many volts they were producing I'm not sure what the voltage is, a couple of thousand volts or something they produce. And so he got his, again, quite some time ago when this happened, so he got a megameter and, sorry, an avometer, not a mega, an avometer, the ones you've seen before, we had to look at yesterday, so that's how long ago it is. And what had happened is he had set it to ampere and not to volts. So he thought it was still set on volts and he didn't check it. And so he put the leads across one of the phases. So it's a three-phase current that was generated from the generator. And obviously from the generator side there's no fuse. Or in those days there were no fuses, no tripping or anything. So it's the full power the generator could produce. Now what happened is there was so much current going through the leads that the leads burnt up instantaneously and generated a UV flash. So even though he wasn't shocked, I mean he was shocked, but he wasn't killed by the shock, he had a UV flash and the front of his body was all burned. And they put him to hospital and he died 3 days later. It's one of the extreme stories where something has gone dramatically wrong, and it was just, he didn't look out, and he had connected the leads to ampere, and the meter was set to ampere as well. And if he had paid a little bit more attention, and he would have just used the voltage settings and the leads were in the correct sockets, then obviously this wouldn't have happened. He would have just taken a reading and he could see, yeah, everything is fine. The generators produce the right amount of voltage. Right, just a little story, little gory story, which quite scary when you hear this. My granddad, he also worked within the electricity industry. And he had like similar stories to tell, tons of them, where things have just gone badly wrong and people had accidents and so on. And when you listen to these stories, you gain a little bit more respect. The problem is when you work in an industry and you get away without getting the odd shock here and there, you lose respect, I think. And you have to remind yourself and always, be fortunate, be happy that you haven't had a shock and that you haven't suffered anything like that. But there's always a first time, and the longer you can avoid the first time, the better it is. And so it's always good to remind yourself how dangerous it is. What we are working with when we deal with electricity and when we are working with it. Okay, what to do with ammeters? Always have some spare fuses for your digital multimeter available or nearby. And what I found as well is that most meters, because it's a common problem that the fuses blow, they've got a bunch of spare fuses inside the meter. So when the fuse is blown and you haven't got any spare fuses, it's worthwhile to just open it up. And some of them have actually got a spare fuse inside, so you just need to swap them out and you can carry on working. So it's just something to bear in mind. Right, measuring current using a clamp meter. So that's a little bit more industry standard. Obviously you don't want to take circuits apart and redirect them through your meter. You want to be able to take a current measurement without having to cut into the circuit. So there's no electrical contact necessary. It's ideal for measuring high levels of current. So if you're looking for milliamps and microamps and things like that, they don't work that well, and I don't think they can read it. And there's any precision or any accuracy for low levels of current. They're very safe to use. So literally all you do is you just have this clamp and you put it around the wire, as you can see it in the picture there, and it picks up on the magnetic field that's generated by the current. You don't need to worry about blowing fuses. The meter is unlikely to blow up, even if there's a really, really high current going through the wire. And that's it. Fairly straightforward thing. I bought myself recently one from China for, I think it was $5. I mean, I never had to use them to that extent, but I thought, why not? It's good fun. Get one. So they are not, obviously, don't use them for work, not this cheap stuff. But if you just want to play about with them and you haven't got access to them at work and you want to see, how much current you're using on your computer at home, or how much does a TV take, or whatever, stuff like that is actually quite good. It's quite good to familiarize yourself with the equipment and, learn how it all works and how it all fits together. Okay, voltage measurements. Voltage measurements are across a component or across a supply. Yeah. So you can see this in the picture here. Just follow the mouse. So you've got your battery, you've got your bulb here. You want to know what is the voltage across the bulb or the battery, and you will get a reading straight away. So it's fairly straightforward, and I doubt that you've got any problems in checking this and doing this. You have to ensure that probes are plugged into the correct socket. So again, with this meter, you can see it here. If you follow the mouse, there's a little ampere socket, and there's the voltage socket. And common is always where the black wire goes, and then the red one goes in one of the other sockets. Again, the meters we've got at the PMC, I think they've got 4 sockets. So it's low current, high current, common, and then volts and ohms. So again, you need to always make sure you put it in the correct circuit. And then obviously, make sure that the correct range is selected. So some, they've got an auto range. I don't like them that much because they tend to take quite some time to come up with a reading. When you predetermine the range, what you tend to do is you start from the highest range if you haven't got any idea what the voltage reading is going to be, and then you work your way down until you get a reading. But most of the time, if you check a battery, it's going to be somewhere between 0 volts and 2 volts. For a battery, if it's a lithium battery, it could be going up to about 5 volts. And so you just select the appropriate range, either 2 volts, 20 volts, or 200 volts or something. And then you take your measurements. It doesn't matter. This is the beauty as well with DMMs. So if you select 2 volts, you will just get an out of range reading if the supply is, let's say, 100 volts. But you've selected 2 volts. You just get an out of range reading, and then you click up until you get there. So the meter is not going to blow up or suffer any damage. That's the digital meter only. Analog meter, different story. Okay, power measurements. Power is a function of V times I. So that means you have to do both. So again, voltage, we were measuring across a component. And then for current, we were measuring the electricity flowing through the circuit. So one is across and the other one is through the circuit. One across the circuit, the other one through. Now for a power measurement, we have to do both. So that means, like in this instance, you can see we've got the sort of the same thing like the clamp meter, where it just picks up on the electromagnetic field. And then we would have to have a couple of wires across as well, and we can see the voltage here. It tells us the current, and then it does calculation on power, how much power is being used. By the way, you can get these modules. They are fairly cheap. I think they are sort of somewhere between a 5 and a 10er. Used to be from China. I'm not sure how much it's going to change as the markets open back up again, and you can get stuff that gets a bit more expensive. I was looking for gadgets recently, and I noticed that a lot of stuff has actually gone up in price. So I'm not sure whether this is going to be a permanent fixture or not. I'm talking things from China. Right, next one is capacitive measurement. So we're going to go into a whole different arena. So this is all fairly straightforward, I think. When you go to capacitive measurement, it's a little bit more, capacitance measurement, it's a bit more difficult, especially the way they measure capacitance. There are about 2 ways of doing this. And also for yourself, to validate whether a capacitor is working or it's broken. You can do this with just a normal DMM, but you need to know what's happening with the capacitor. And you can't really determine the value of a capacitor, but you can pretty much say, yeah, it's okay, it still works, or there's something wrong with it. Okay, the first method is that it's based on the time constant. So the time constant is the time it takes for the capacitor to charge up through resistance. And so typically you're looking at T or tau, which is the formula for the time constant, is C times R. So it's capacitance times resistance. And for a capacitor to charge up, it takes about 5 time constants to go up to about 99%, around about there. Okay, so you could do a whole calculation, what is the capacitance, and then you apply resistance, let's say a mega ohm or something, and then you put a voltage across and you look until it rises up to, put 12 volts across and you look until it rises up to 12 volts. And then based on the formula, you can work out what the capacitance is of the capacitor. So that's one way of doing this. What you will be doing realistically is when you've got a single phase motor, you will find inevitably a capacitor in there, and if something is wrong with the motor, a quick test with the capacitor is you just put your meter, you isolate the capacitor, you take it out, you disconnect it from the terminals, or at least one side, then you put your meter across the capacitor and you wait for it to charge up. And what you will find is that initially it's got very low resistance, and then the resistance slowly goes up and up and up and up, and eventually it'll be almost like a couple of mega ohms and so on. So if this is happening, if you can see this with a capacitor, using a DMM, then you kind of know that it's most likely okay. So the capacitor is working, and it may not be the correct value, or it's going to be very difficult to determine the value using this method, but at least you know it's working. If you get a short circuit, or you get an open circuit, like nothing is going in, nothing is coming out, then you know there's a problem, and it's most likely the capacitor is broken, and all you need to do is change the capacitor, and the motor is going to work again. Right, number 2, reactance of the capacitor. Reactance or apparent resistance changes with frequency. The higher the frequency, the lower the reactance. An AC signal is generated, passed through the capacitor, connected in series with the resistor. The voltage drop will determine the capacitance. Okay, it's a lot of text, and it's a bit complex to go through. Let me just sort of put this in simple words, and that is that a capacitor reacts to frequency. At DC conditions, a capacitor has got infinite resistance. It's like a piece of rubber. When you put a high frequency across a capacitor, it just operates like a piece of wire. And then, depending on the frequency, you've got a resistance somewhere in between, between virtually short circuit to open circuit, and anywhere in between, depending on the frequency you're putting through. So if you've got like a resistor with a capacitor in series, you can actually work out and then based on the signal you put in, you can actually work out the capacitance, and it works fairly well. I don't expect you to do this, and so I do this with my H&C students. I make them work out a capacitance, a blind capacitance, so they get a capacitor, can't take the readings, and they have to go through the process, a long process to get like a variable resistor, a signal generator, and a couple of DMMs, and then they have to work out what's happening inside a meter that works out the capacitance bridge. Right. Just stop for a moment, get some breath. And Brett had a question: how accurate is the clamp meter? For high currents, I think they are okay. They're reasonably accurate. Obviously, it's always a problem when you pick up a magnetism. You get magnetism all over the place. And when you do this in an environment, so if you're in a factory and you've got like a cable trench, and you've got cables next to one another, and you just select one cable, I would imagine that the readings may be slightly skewed with all the stuff that's going on there within the magnetic spectrum. For low currents, I don't think they're very accurate at all. High currents, a little bit more. So if you're interested how many amps are going through, they're great. If you're interested how many milliamps or microamps, I don't think they're very good. It's too low, too little of a magnetic field to pick up on that. I think the lowest resolution, if I remember right, was about a tenth of an amp, so it's about 100 milliamps. That's the lowest resolution they go to. So for the clamp meters. Right. Any questions? So I'm gonna wait a little bit. Just get some breath. Let me just type it in. So. Okay, thanks, Callum. I think it's about half a minute delay, so just looking at this. Okay, good. Thanks, Declan, for the reply. Okay, all right, wrong keyboard. I've got two keyboards here, two computers. One is which I use for the chat room, the other one which I use for the presentation, and that runs on two different computers. Capacitance bridge. That's again one method which was used in the olden days, and the principle of operation is still the same when you buy a modern meter, even a digital one, to determine capacitance. The way this works is you've got a known resistance on one side, and then you've got an unknown capacitance on the other side. And what you do is you try to zero, in your meter you try to get zero to balance it out, and once it's balanced out you can then pretty much read off what the capacitance is. So that's what was done in the olden days to determine the capacitor. And it all works on this formula here, which is XC. XC is a reactance. We talked about this earlier. So reactance is like an apparent resistance. It's a resistance which doesn't really exist, but it seems to appear as soon as you apply this element of frequency, F, into the equation. It's like a capacitor. Normally it's got a resistance of a piece of rubber. And and when you apply a frequency, suddenly that thing starts to conduct. The capacitor, that's here, C starts to conduct. And it looks like we've got some sort of resistance with our capacitor. And this is a formula, so we've got XC is a reactance, it's measured in ohms, same as we measure resistance. And then F is frequency, C is capacitance, and this letter pi is 3.14, and then another 200,000 figures at the end of it after the decimal point. But it's 3.14, that's what I always use, 2 times 3.14 times the frequency times the capacitance, and it's all taken over 1, or 1 over. And again, when you sort of look at this, so if the frequency goes up, XC goes down. If the capacitance goes up, XC goes down as well. So big capacitor, high frequency, that value comes close to 0, like a piece of wire. Okay, if this becomes 0, or any of these items become 0, so frequency is 0, so that would be when it's DC, then XC will be infinite. So it would go to infinity, infinitely high resistance. Okay, let's move on. Easy way to check capacitors, to find out whether capacitor works, so it's that. Use a DMM, choose the resistance setting. A small voltage will be applied to the capacitor. That's automatically from the resistance setting. It'll charge up slowly. As it charges up, the resistance reading goes up. So initially you will get, so you short out your capacitor, put your meter on in resistance setting, and initially it'll be going down to almost 0 ohms as it gobbles up all the current that's available. And then as the capacitor charges up, the charge up time will be slower and slower and slower, and then it'll go to a couple of kilo ohms and a couple of mega ohms and so on. And it'll slowly charge up, and you can see if it's an analog meter, you will see the needle rise very, very slowly, from a low to high resistance. If it's a digital meter, the same thing, it'll just go up very, very slowly. And that's one way how you can sort of quickly determine whether the capacitor is still working or not. So if it doesn't do it, then most likely something wrong with it. If it does do it, doesn't mean it's okay. It might still be struggle when MEMS and capacitors. So a lot of the MEMS will have a range for testing and measuring capacitors. And it's really, really bizarre. For coils, it's very, very rare that you find a digital multimeter that can measure coils, even though they are measured in a very similar fashion to capacitors. They've got a similar bridge. But there are a lot of DMMs around which have got like one session for capacitors, so you can measure capacitors as well. You've got a couple of, they call it an LCR bridge, so they are meters which measure the inductance, capacitance, and resistance, and that's what they look like. And there's one as well here. I bought a similar one. I think you may have seen it. I got it from China for £5, about £5. And it works really well. These bits here, if they are made in the UK, there's one company. I think I've got a picture of them. Have I got a picture? Let me just see. Oh yeah, here it is. It's Peak, this company here. So they do LCR meters. They are made in the UK, and they are about £100. So they're quite expensive. That thing here is about £1,000. And then it depends where you get them from. They're somewhere sort of the £100 range. And that's exactly the same thing I've got. It's called a component tester. And I got it from China for £5, including postage, packaging, and everything. Plus, I think I got like a little casing for it as well, and plexiglass. And that was, I think, about £2 or something. But it works really well. I got the second one, the first one. It dropped and I didn't have a casing. And I cracked the display, so it dropped off my shelf in the workshop. So I bought a second one, but this time with casing to try and protect it a bit more. Okay, let's go back. Let's have a look at an inductance meter. So with inductances, it's really the only way to test an inductance and to work out, what is the inductance of a coil, is to use something that's similar to a capacitance meter, but it works the other way around. So the way a coil works is that in DC conditions, a coil is just like a piece of wire. And when you apply AC to a coil, an alternating current, suddenly you find that there's some sort of reactance in there. So it's the opposite way around to a capacitor. So high frequency, high reactance. So if you've got a very high frequency, a coil is almost like a piece of rubber. So high frequency signals don't travel through a coil very well at all. And so they both work in opposite ways. So the higher the frequency, the higher the inductance. And there should be a formula as well. You can see this here. So XL is omega L. I just stick this in here. Omega is just 2 pi F. So this is omega, and that's what it stands for, 2 pi FL. So XL is equal to 2 pi FL. So it's almost the same formula as for the capacitance. The only difference is there's no 1 over the whole expression here, but it's just XL equal to 2 pi FL. Right, what have we got here? So it's again the same thing. You've got your inductance bridge, and you would have like your unknown value in here. So you would have your selection on this side and on this side as well. So you would normally sort of click it around, and eventually this would go to 0. And then you could read your capacitance of the inductance bridge. So that's the olden days. That's how it was done in the 1920s when they try to figure out the inductance of a coil. Modern days, obviously, we would have our LCR meter or marvelous gadget from China, or go the full hog and is this one from Farnell or something? You can go to Farnell or RS Electronics and you can spend about £1,000 on one of these units here. And obviously, probably the precision is a lot better than the £5 device. And I've noticed as well there are certain things it doesn't test very well or it gives you wrong readings, obviously wrong readings. And they are very precise, and also the Peak ones, they are very precise as well. There's a difference whether you pay £5 or £100. But But then again, I mean, in my instance, I thought, how often do I measure a coil? And it's just a little bit, for demos in class, and then it's for myself once or twice a year. There's no need to go crazy and get something for £1,000 when a £5 for my purposes will be more than sufficient. Again, I would recommend this to you as well. This is a component tester. It tests transistors, resistors, diodes, Zener diodes, light emitting diodes, coils, capacitors. You just stick them in here. So one leg goes on this side, the other leg goes on the other side, and you get your reading, and everything is fine. So it just tries to detect what it is and then give you an indication of what you're dealing with. If you do anything down to component level, which I doubt you will do at work, but if you get interested in electronics and you just want to take it a bit further, why not? I mean, it's a fiver. It's how much you pay for a packet of tobacco these days, or a pint? It's maybe 2 pints. What's my passion? Biscuits. Then again, biscuits are cheap, aren't they? 10 packets of biscuits, and you get one of those meters. It doesn't work quite as well. Anyway, that's what it looks like. I think you've seen it. That's the one I've got. That's the plexiglass glass housing. I don't have any shares in the company in China who produces these things, but I think they're just marvelous. And for the price they charge you for them, it's nothing. I had tons of pleasure out of it, testing stuff and using it, and I probably got my £5 worth of fun out of it many times over. How to measure coils and caps? Okay, to measure in inductance or capacitance, it is important to isolate the component from the circuit to take the measurement. So when you, for example, measure a capacitor and it's in your single-phase motor, you need to disconnect at least one side of it and take it away from the terminal. Otherwise, you've got an inductance in there as well, with the coils where it's connected to. And so you get like all sorts of freaky readings which don't make any sense whatsoever, and the meter will not be able to interpret it either. So you need to isolate one of the sides, and then you can put your meter across it and you can take a reading. It's very important. Same with the coil as well. So you have to isolate one side of a coil. So if it's a 3-phase motor or even a single-phase motor, you have to get rid of all the terminal plates and make sure that each coil is not connected to anything else, and then take your readings. That's really the way to do it. Let me see if I got... you can see this here. You've got your coils. You've got U1, U2, V1, V2, and then you've got W1, W2. Yeah. Most motors, 3-phase motors with the 3 coils, they're configured in this fashion here. Yeah. So they go across, and then the last coil goes all the way across like that. You can see those terminal plates here. So if you wanted to take measurements, you would have to take those plates off. Either look this up somewhere or have this in your mind, and then you can measure from there to there, from there to there, if you follow the mouse, and then from there to there. And you get measurements for each of the coils. So you could do, obviously, an inductance test as well on your windings, and you will get a reading. And if your inductance is vastly different from any of these 3 coils, there's a good indication that something got shorted out, and that the coil maybe has only got half the inductance. Obviously, you can do a resistance test that does the same thing, and it gives you a good indication that something is not quite right. Going sort of back in industry, I don't think I've ever measured the inductance of those coils which are in my motor, but you could. You could do it. I mean, normally if you test them, it's like you say. I think I was talking to some of you guys when you sort of take measurements that you do your inductance test. When you take measurements on a motor is slightly faulty, what you would do is you would just get rid of it and put another motor in. You wouldn't spend too much time on trying to fix it or whatever. But it's just something you could do if you ever have to. If it's a big 3-phase motor, And it's not like one of the small dinky ones, but a really big one that's worthwhile before you throw it away to find out what the fault is. And for big three-phase motors, you might be looking at thousands of pounds as opposed to about 100 pounds for a smaller one. Okay, disconnect one side of the capacitor. That's connect your LCR meter and take a measurement. So that's for your single-phase testing. And again, if you haven't got an LCR meter, you can just do the test with the DMM in resistance setting and see whether it charges up. Okay, and we're going to look at the frequency meter. Frequency is defined by recurring changes per second, so that's your frequency. Yeah, you can see this here. So we've got about 50 of these cycles in 1 second in our power supply. And again, we look at the frequency counter, frequencies where we've got them. We've got a couple of examples here. So 50 hertz, so that's 50 changes per second. That's your power supply. In America, it would be 60 hertz. We've got 1,000 hertz or kilohertz, which will be audio, for example, a whistle. Can I try it? Let me try it. So that's roughly about 1 kilohertz. Yeah. And that's actually true. I did measure it. It's about 1 kilohertz. So that's what 1 kilohertz sounds like. When you go on a phone, the traditional old landline telephone, the frequency which goes through a phone, or which a phone is capable of dealing with, goes up to about 3.4 kilohertz. Yeah. You can hear realistically up to about 15 kilohertz, and supposedly up to about 20, but it's unlikely. The older you get, your hearing drops. Once you are at pensionable age, you'll probably only be able to hear about 10 kilohertz, 8 kilohertz. But the phone only uses up to about 3.4 kilohertz, and that's normally enough for the voice spectrum to be intelligible. We've got radio as well, so 98 kilohertz is BBC Radio 4 on long wave. Then medium wave, there's one frequency which is 1215 kilohertz, which is absolute radio on medium wave or AM radio. 27 megahertz CB radio, probably your parents will know about this stuff. 100 megahertz is classic FM or FM radio. Yeah. Then 1000 megahertz, that's your mobile telephone, and then you've got actually, to be precise, is about 900 megahertz. Then there's 1800, 2100 megahertz, and 2300 as well now. So there are a lot of frequency bands which are made available for mobile phone. And then 10,000 megahertz or 10 gigahertz, that's where you get satellite television. So when you see those dishes on people's walls, they're tuned in to about 10 gigahertz, and it goes up to about 14 gigahertz. You've got a spectrum here, and it goes up and up and up and up. Then we've got a massive, huge infrared light spectrum, and then we've got visible light as well, which is an electromagnetic wave, but it's very, very short wave. And then you've got X-rays and gamma rays, and that's sort of the dangerous stuff. And UV light as well, which is not good for us. Okay, this is a radio bands. So you've got AM radio, shortwave radio, then you've got FM radio, and then mobile phone and so on. And this is how a frequency meter works. So you get your signal in, which is going up and down. Then you've got a sine wave or pulse conversion, so just pulses are generated. And you've got a gate and a counter. So this gate opens up, and it takes a count of the number of pulses which are coming through. And then you've got a clock here as well, so the clock just opens it up. And then this counter is connected to a display. And you get an indication of how many pulses were counted in a given period of time. Again, the big question, what do we use them for? What do we need them for? I'm going to show you in a minute. So that's what they look like. They're frequency meters or frequency counters. So the syllabus calls them frequency meter. I've never heard frequency meter. I've always heard the term counter, frequency counter. So that's all they are really. 450 megahertz. Just an example here. That's the so-called UHF, and you get a little bit higher the TV band starts, and here you get commercial industrial two-way radio systems, which work around about there. Okay, there's a frequency meter as well here. That's what they may look like, and it just shows you what's coming out. This is sort of fairly modern stuff, a bit more complex, so you can look at the waveform as well. On some devices, some multimeters, you've got an option for frequency, and they don't tend to measure high frequencies. It's mostly just lower frequencies. So 50 hertz, 100 hertz, up to maybe a couple of kilohertz. But that may be enough for the purposes you may want to use it for. Okay, so it's just sort of the audio spectrum, what you can hear, and maybe for three-phase motors when you've got a VFD, a variable frequency device, so you can measure what frequency is coming out of it. A few more frequency counters you can see here. Again, if you try to buy them, they are you get very cheap versions these days, which is just a bit like this one here. It's just a chip and a little display, and you can probably pick them up for a couple of pounds on eBay. Then the commercial stuff, you're looking again at about £1,000 plus. Okay, it's almost like a frequency counter. It effectively does the same thing. It just counts pulses. And this is an RPM, revolutions per minute counter meter. So if you have an electrical motor spins round, you want to know how many RPM the motor is doing, then that's your meter. So it looks at, sometimes you may have to put like a little chalk mark or something on the shaft, and it just looks for this change, this recurring change to take place, and can work out the RPMs. The concept is very straightforward. It's essentially just the same thing as a frequency counter, but it's just made for RPMs, or for lower frequencies. So it doesn't measure like 1 million cycles per second, but just a few thousand cycles per second. Okay. Okay, this is an application. So we've got a VFD. So a VFD is normally hooked up to a three-phase motor. We use it for starting a three-phase motor, especially if the motor is not a self-starter, and also for varying the speed of a three-phase motor. And again, if you wanted to make sure that thing actually works and is putting out the correct frequency, in those instances you would need a frequency counter. And obviously you can measure the frequency on here, and see what frequency comes out, and then you can measure, using the RPM meter, the frequency on the shaft of the three-phase motor, and you can then come up with a conclusion of whether it actually is running at the same at the design frequency, or it isn't. And if it isn't, there's something which is called slip, and that's for asynchronous motors. Synchronous motors don't have slip; they should lock onto the correct speed. Asynchronous ones, they need to have some slip. So that's the difference between the design frequency given by the VFD and the actual revs per minute as you find them on the motor shaft. Okay, power factor. So this is when you measure power factor. Did we do this before? We did this before. I think the slide just moved down there somewhere. But you can see this as well. We've got the power coming in. We've got the watt meter here. We've got an ammeter. And then we've got the load. Okay, anyway. Power factor meter. No, we've got it here. So that's again what they look like, your power factor meter. So power factor means how much phase shift have you got in your system. Phase shift is when the current peak and the voltage peak are no longer aligning with one another. So that's a bit of a problem, if they don't align. And the problem is you lose the efficiency of the system. And normally, this happens in every factory. Factories tend to have loads and loads of motors. Motors are inductive, so the current is going to lag the voltage, sort of staying behind the voltage, and you get a little bit of a phase shift. And in order to compensate for that, you will find that your companies at Hovis, Coca-Cola, at Princess, you will have big cabinets full of capacitors, and capacitors are switched into the supply to compensate for the power factor, to sort of realign the maximum current with the maximum voltage, and to make sure you get the most from the electricity you buy from the grid. Okay, and that's the presentation. What's the time? Yeah, it's about right, about an hour. Describe tests you would take to test a capacitor in a single phase motor. What are the two methods? And using a DMM, what would you have to do to measure the current flow out of a battery? What happens to a DMM if you mistake the polarity of the probes? Okay, let's start off with the first one, and then we'll be done in about 10-15 minutes. Describe the steps you would take to test a capacitor in a single phase motor. What would you do? Somebody. Come on, guys. Obviously, I need to wait a bit. It's a bit of a delay. Good point. Disconnect it first. After disconnection, what would you do? Let me just type it in. Get the right keyboard. Okay. Right. Obviously, this is slightly delayed. So, right, one method. Give me one method of what you would do to test a capacitor. Easy. What would you use? What sort of instrument? Right increase. Disconnect one side of the capacitor. Use the DMM on the resistance setting. Charge it up slowly. The resistance should become... Okay, spot on. I'll put the meter over the capacitor and... What did you charge up? Okay, spot on. Right. Watch it. Yeah, spot on. Yeah, watch the capacitor. See it go up. What are the two methods to test the windings of a three-phase motor? So what could you test for in a three-phase motor for the windings? Insulation test is one, yeah. Resistance test as well, yeah. And continuity, okay, fine, that's it. Hey, thanks Sam for coming in. Continuity, spot on. Thanks Declan. Okay, yeah, Ryan, spot on, yeah, for insulation test. Thanks, Brad, across each winding. Okay, next question is how to measure The power consumption. Okay, Nick, good point. Remove the links, yeah. Very, very important, yeah. You need to isolate all the coils before you take any measurements. Otherwise, it's all skewed up slightly. How to measure power consumption with a simple DMM. Okay, fine. Voltage and current using a clip-on ammeter style DMM. Yeah, that's okay. Especially when you're dealing with high currents, then work on the voltage. Yeah, okay. Spot on, Hayden. Okay. Right. Need to get the right keyboard. Last two questions, and then we are done for today. Using a DMM, what would you have to do to measure the current flow out of a battery? Again, the key thing about a DMM, that maybe two little bits you have to do for that. This should be a Callum question. Callum, can you answer this? How do you do it? How do you measure current flowing into a circuit from out of a battery? Okay, Sam, going ahead, charging ahead. It's spot on, Sam. Yeah. Nothing happens really. You just get a negative reading, but the meter doesn't blow up or anything. Yeah. So you're okay. But thanks, Sam, for that. First question: how do you measure the current coming out of a battery? Anybody else? I don't know whether what's happened to Callum. Anybody else? Just give us an answer, and then we are done for today. Anyone for the first question? Give it a go. What do you have to do? What do you do with the meter? Where do you put the terminals in? How do you measure it as far as the circuit is concerned? What do you have to do to the circuit? Okay. Good question then. Let me just go back. Lost. Wrong keyboard. What do you have to do? Right, let's look. Right, no idea. Regan, yeah. Let's have a look. You have to disconnect the battery, connect it up in circuit to the DMM while it's set to amps. Yeah, spot on. That's good. Hayden, can you do the voltage of the battery and then work out the resistance between each? So actually, you could, But you've got a current meter on your DMM, yeah, so you can do this. You don't need to calculate it, but what do you have to do? Do you remember with this image here, with this graphic? How do you measure current? What's the important thing about measuring current? You can, I mean, obviously, you can measure the voltage drop and work out the resistance. If you know the resistance, and then work out the current. Or measure the resistance, work out the current, but a lot easier than that. So, look at the diagram here. What do you have to do? It's a pity we couldn't do this in practical. If we would probably blow the odd fuse here and there, but you do it once and twice and maybe the third time, and you would know for sure what to do with it. And obviously, you just do it for small circuits, low current circuits, not for industrial stuff. Okay. Callum, where are you? I think by the sounds of it, you've done it before, so you should be able to explain what do you do to measure current. Anybody? Nobody? Yes, no? Okay, use a multimeter as an ammeter and put in the circuit. Okay, spot on, Hayden. That's correct. What do you need to do with a multimeter? Okay, Ryan, spot on. What do you have to do with a multimeter? What's very important? I'm talking about the leads and the multimeter. Okay, still a bit of a break. Okay, Callum. That's only for volt readings. That's Callum, that's the reason why the fuses went in your ammeter. You have to break into the circuit, the same as you can see on the diagram here. So that's right. And the current has to physically flow through the meter. And then you get a reading. Yeah. Okay, Callum, in the correct hole, so amps and the correct decimal. Okay, that's fine. Yeah, you got it, Callum. So again, let me just go further to the next diagram here. You've got, normally when you use your meter for voltage and for resistance measurements, you've got the red lead where the mouse is on the right hand side, and the black lead goes into common. Yeah. Whenever you measure current, you have to take out the red lead and put it into the ampere socket for currents between 1 amp and 10 amp, and if it's just low current and you're just looking at a few milliamps, you use the third socket from the right, looking at the diagram. So that's it. Yeah? So that's what you do with that. So that's very important. So if you leave it in the right. Okay, so we've done it. Let's have a look. That's what I thought I was buying the fuse. Okay, spot on. Yeah. Thanks, Callum. You got it. Right. We are done here. So thank you very much for sticking. I'm not sure whether you've got your mentors meeting you at 3:30. Anyway, I'm gonna end the stream, and I will see you. I'll be around tomorrow via email. If you need me to do a session on 308 or anything, please let me know, email me, and if there are several of you, then I make a session and I'll email it out. Otherwise, I'll see you on Monday afternoon. So we've got a short 315 session with the remaining bits which are still outstanding, and then on Wednesday we've got the summary, and then on Thursday we'll go through the assignment brief. Okay, thanks for sticking there and coming online and sticking with me for this time. I'll either talk to you tomorrow or next time is going to be on Monday afternoon. Okay, right. Have a good. If I don't see you before, have a great weekend. Stay safe, stay healthy. And look after yourselves. Very, very important these days. Okay, see you then. Bye bye.